let's look at the motion of the moon around the Earth. So here, Earth, moon. Moon, of course, executes roughly circular orbit around the Earth. Okay. So same as the previous calculation, we can get the acceleration due to gravity. Right, I'm going to draw a little m for moon rather than try and draw this crescent each time. Is g m Earth r Earth moon squared. Okay. So I start off with my force equation and then canceled out already the mass of the moon. So if I had mass of the moon here, this would be equal to force, and then I have a mass of the moon over here, but that's just canceled out. Okay. So we also know that if I have an object moving on a circular orbit, it needs some centripetal force to cause an acceleration towards the center of the system to keep that thing on its circular path, right? So we're going to identify this acceleration caused by gravity with the centripetal acceleration. So acceleration m equals v m squared r Earth moon. And we know also that velocity is 2 pi r over the period, right? Capital T. Okay. So now we equate these two things. 2 pi r over t squared Okay, so we've equated the acceleration caused by gravity to the centripetal force that we know needs to hold the moon on its circular track. So if we plug in all these numbers and this thing equals out, well then we've shown that the force of gravity from the Earth on the moon is the thing that holds the moon on its circular orbit. Therefore, the force of gravity is the force that generates orbital dynamics, that generates the celestial mechanics that we see. So, simplify this to 4 pi squared over t squared equals g mass Earth radius Earth moon squared. So we can find these guys, big G and mass of the Earth, via the Cavendish experiment and then the application of the Cavendish experiment. So we can find both of these numbers. The period of the moon is, I wrote it down, 27.3 days, a lunar month. Which is 2.36 times 10 to the 6 seconds. And then, as I mentioned before, the distance between the Earth and the moon was known even to the ancient Greeks. (384.4 times 10 to the 6 meters). Right. Not they didn't know it so accurately, but they had a rough estimate. Right. That was actually pretty close. And if we plug in all these numbers, we end up with, I'll just write it so it seems real. 7 times 10 to the 12 equals 7 times 10 to the 12. Negative 12, excuse me. So we can see that because this equation equaled out, it is indeed the force of gravity that holds the moon on its circular orbit. Okay. Pause for questions. Okay. So let's talk a little bit about orbits. Let me get my notes real quick. So we mentioned briefly that before Newton, the laws for the orbits of planets around the sun were known, right? So I'm just going to intro them a little bit right now, and then I will talk about them more next class. So this is about 70 years before Newton. Okay. Along came Johannes Kepler. And he published his 3 laws of planetary motion. Things getting kind of hard to read. Switch. Okay. So these are empirical laws. And what I mean by empirical is that they were not derived from first principles. You didn't sit down and think, okay, I know these forces at work, how can I derive equations that show me how the planets move, right? Like we do in class, for example, when is that marble block going to tip over? When is this thing equal to the other thing? How much force, blah, 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 blah. He didn't do a calculation like that. What he did was he observed the stars and planets every night for pretty much his whole life, right? He kept a very accurate record over a very long period of time about how the planets moved, and then, based on these measurements, was able to find these laws that were really just him writing down the equations that made all the numbers fit, right? He didn't know where the equations came from, but he knew they were true via observation. So he had 3 laws. I'll write and then speak. Rule number 1, closed orbits are elliptical with the sun at one foci. So if we were to draw this, and I'll talk more about the shapes of orbits next class, we would have an elliptical orbit, sun at one foci, and whichever planet we're talking about goes around on this orbit. And you might think, well, aside from Pluto, which isn't even a real planet anymore, orbits that we see are mostly circular, right? Well, a circular orbit is just a special case of an ellipse, right? Where the ellipticity is shrunk down to nothing, right? Where it becomes a perfect circle. We still, in principle, have an ellipse. It's just an ellipse with no ellipticity. Okay, so this is when we take the limit of that shape. And in fact, although a lot of orbits look circular, they do have some small imperfections, some small ellipticities to them. So what Kepler said was that all the closed orbits, all of the orbits of things that stay inside the solar system, right, are elliptical with the sun at one foci. The next one is a little tricky to understand. Orbits sweep out equal areas in equal times. So this is about the speed at which orbits take place. So as a planet follows this elliptical orbit, it doesn't do so at a constant velocity. It slows up and speeds down. And Kepler found that the mathematical relationship between the speed was given by this sweeping out of orbits. So imagine we have time 1, it's not a 1, time 1, the planet's there, time 2, the planet's there. Okay, so we have in between some delta t. Now we imagine that attached between the sun and that planet, there's a line. Okay? And as the planet moves around on this orbit, this imaginary line sweeps out an area. So we'll call this area A. Okay. Now later, this planet has moved to another place on its orbit, say here, so we'll call this T3. Now there's still that imaginary line attached to it. Now if we ask the question, how far will this planet move in this same amount of time that it took it to move from here to here? How far has that planet gone? Okay. It has to go the same amount of distance such that it sweeps out an area that's equal to this area. So this planet has to move much further on its orbit to sweep out that same area because the line is much shorter. Right? When the planet is near the sun, this line is shorter, so this area, in order to be the same, has to have that line that defines it dragged over a larger distance in this orbit. So this progression from T3 to T4 takes that same delta T that it took it to get from T1 to T2, but the planet's moved a much larger distance in order to make those areas the same. So what this second law is saying is that orbits are slower when they're further away from the sun and faster when they're closer. And number 3, I'll just write it mathematically. The square of the orbital period is proportionate to the cube of the semi-major axis. Okay. The period, of course, is how long a full orbit takes, right? And this distance, the semi-major axis, right? If we were talking about a circular orbit, that would just be the radius, but semi-major axis is well, I'll just draw it. We'll talk more about this next class when we go over conic sections. So we have the semi-major, or the major axis goes from one side of the ellipse to the other. The minor axis does the same thing, but in the shorter direction, and the semi is just half of that. Right? So semi means half. So if you could see if this was a circle, if I squished this together until it was a circle, that semi-major axis would just be the radius. Okay? But when we're talking about elliptical orbit, it's this distance here. So these are the 3 laws that Kepler came up with that showed how planets moved. Now, next class, we'll talk about how do we get to these laws from the knowledge that Newton gave us about gravity. Okay? We'll actually derive these guys. Okay. So this is the proportionate symbol down here, right? Which means that if I wanted to write this in equality, there would be some constant in there. That constant wasn't known to Kepler. Well, I mean, it was known, but the numbers that made up the constant were not known, just the result. So we'll see next class that with the derivations that we can do thanks to Newton's law for gravity, we can find that constant just by deriving it. Okay. All right, if you have any questions, go to the Reddit forum and ask them. Finally, someone asked a question and I got to answer it, which felt very nice, made me feel important and needed. So keep asking questions. All right, again, I hope you're all doing very well, and I will talk to you soon. All the best.